Hello everyone, welcome back to the session of Material Science. Myself Rahul Mane, I am working as Assistant Professor in the Department of Electrical Engineering KKWAG, Institute of Engineering Education and Research Nasik. Today I will discuss unit number 4, that is magnetic materials. So before this already we have covered unit number 1, 2 and 3. So in Unit number 1, we have covered the properties and applications of dielectric material. Then in next unit, we have tested that dielectric material, and after that, we have seen the properties and applications of insulating materials. So in the similar way, in this unit, we are going to discuss the properties and applications of magnetic material and applications in terms of electrical equipments. So learning outcomes for the sessions are, at the end of the session, learner will be able to find out the parameters of magnetic materials and to compare the magnetic and dielectric materials. So prerequisites for the sessions are some concept from the magnetism and parameters of dielectric material, which is from unit number first. Now this concept is required to compare the dielectric and magnetic materials. So let's quickly introduce the magnetic materials. So magnetic materials plays very important role in modern technologies like magnetic memories, compact disc or tapes, televisions, motors, generators, transformer, telephones are some of the examples of applications of magnetic materials. So after these introductory sessions, we will try to find out the parameters of magnetic material, and then we will differentiate between the magnetic material as a soft magnetic material or hard magnetic material, and also the classification of magnetic material based on the parameters of magnetic materials. Now moving ahead towards the parameters of magnetic materials. So already such term is present in unit number 1, that is dielectric material, and in that unit we have seen the parameters for dielectric materials also. Okay, so that parameters can also be discussed here, and we can compare the parameters which are applicable for the dielectric material as well as the parameters which are applicable for the magnetic materials. Okay, so first parameter for the magnetic material is permeability, second one is magnetic dipole moment, third magnetization, and fourth magnetic susceptibilities. Okay, so these are the four parameters which are applicable for the magnetic materials. Now let's quickly revise the parameters which are applicable for the dielectric materials. So parameters which are applicable for the dielectric material is first permittivity, second dipole moment, third polarization, and fourth polarizability. Okay, so we will see the some similarity structure between these parameters for dielectric as well as magnetic materials. Okay, so here permittivity is there, here permeability is there, here dipole moment, here magnetic dipole moment is there, here polarization, here magnetization, and here polarizability, here magnetic susceptibility. Okay, so we will discuss the one by one parameters which are applicable for the magnetic as well as dielectric material. So let's quickly revise all these parameters which are applicable for the dielectric material, and we will quickly shift towards the magnetic materials. Okay, so first parameter is permittivity, and which is applicable for the dielectric material and which is shown with the help of symbol epsilon r, and it can be defined as the ratio of capacitance of a capacitor with the dielectric material between the conducting plate to the capacitance of a same capacitor, to the capacitance of same capacitor with vacuum as a dielectric material. Okay, so since it is a ratio of two similar quantities, means capacitor, so this term is a unitless, so it does not have any unit. Okay, so we know that, and we have discussed these terms in unit number 1 as permittivity is unitless. Okay, so this is the first parameter which is applicable for the dielectric material, and now on the basis of this permittivity we have to define the permeability also. Okay, to understand this term definitions, epsilon r is equal to c divided by c0. Now moving towards the second parameter for dielectric material is dipole moment, and we know that dipole moment is represented with the help of symbol mu, and it is given as whenever two charge of equal magnitude, so let's consider here I am having plus and here I am having minus, so two charge of equal magnitude but of opposite polarity which are separated by some distance d, then there is existence of dipole moment and which is given as q into d, where q is nothing but charge and d is nothing but distance between them. Okay, so obviously their unit will be coulomb meter, so coulomb will be for charge and for distance it will be meter, so the unit will be coulomb meter. So this is the second parameter for for dielectric material, that is a dipole moment. And on the similar hand we have to explain the magnetic dipole moment and we have to compare the electric dipole moment and magnetic dipole moment. Okay, so this is the second parameter for the dielectric material. Next parameter for dielectric material is polarization, which is denoted with the help of symbol P and which is nothing but the dipole moment mu per unit volume is nothing but polarization which is taking place in a dielectric material. So again, so on the basis of this polarization, we have to define the magnetization also and we have to compare the polarization and magnetization. And finally, fourth parameter is nothing but polarizability, which is denoted with the help of symbol alpha. And this polarizability is nothing but ability of material to get polarized. In the similar ways, here we have to find out the susceptibility of a magnetic material, which will gives us the ability of any magnetic material that how it will get or in what amount it will get magnetized. Okay, so I hope we have quickly revised all the four parameters which are applicable for the dielectric material, and based on this again we will discuss all these parameters which are applicable for the magnetic material and we will try to relate between these parameters for magnetic as well as dielectric material so that it will be very easy to get understand. Now moving towards the first parameter of magnetic material, that is nothing but permeability. Okay, so which is analogous to permittivity in case of dielectric material. So in order to understand, here I will quickly revise the concept of permittivity, which is denoted with the help of symbol epsilon r, which is equal to C divided by C0 and it is unitless quantity. Okay, so this is for dielectric material. Now we will see about the magnetic material. So here, the permeability is nothing but the property of material which allows itself to get magnetized. So this word is important. That is the property of material which allows itself to get magnetized is nothing but permeability of that magnetic material. Or in simple language, we will understand this. It is a readiness of material to accept magnetization. It is a readiness of a material to accept magnetization. Okay, so this is nothing but permeability of a magnetic material. And here one more important term is there, that it is varies from material to material, means for each material the value of permeability is different, and again that value of permeability is varying due to temperature and value of saturation. That saturation is nothing but magnetic saturation of any materials. Okay, now it is denoted with the help of symbol mu. Okay, so electrical permittivity is denoted with the help of symbol epsilon r, whereas magnetic permeability is denoted with the help of symbol mu. A good magnetic material should have high value of permeability. So as there is a high value of permeability will be present in any magnetic material, then we can able to design a strong magnetic materials. Okay, so the value of permeability should be high for a good magnetic material. Okay, so next, practically it is observed that for a magnetic material, the magnetic field density B is directly proportional to the magnetic field strength H. Okay, so based on that, so this B and H, we will derive one short relationship, okay, or derivations. And finally, the unit of permeability is Henry per meter. Okay, so the, remember this, the unit of permeability is Henry per meter or it is measured in Henry per meter. Okay, so from this point here in next slide we will derive one short expressions like this. So practically it is observed that B is directly proportional to H, means as I am increasing the magnetic field strength, there is increase in magnetic flux density inside that magnetic material. So let's consider I am having one iron piece, and if I am applying external magnetic field to that iron piece, then obviously this magnetic material will get magnetized, means there is increase in value of B, and here I am externally applying the value of H. So in short, anyone can say that this B and H are directly proportional to each other, means as I am increasing the value of H, the magnetization will get increased in terms of B. And from this, here I have written the expression, and the proportionality constant alpha or directly proportionality constant is represented with the help of mu, and that mu is nothing but permeability of magnetic material, and which is nothing but B by H. Okay. So also we know the small relationship from the magnetism concept, that mu, that is permeability, is also equal to mu 0 into mu r. Like in case of dielectric material, we know the relationship, that is epsilon is equal to epsilon 0 into epsilon r. Okay, so the similar expression is present here. Mu is equal to mu 0 into mu r. So where mu 0 is called as the permeability of free space, having the value 4 pi into 10 raised to minus 7 Henry per meter. Okay, so the value of permeability in a free space is 4 pi into 10 raised to minus 7 Henry per meter. Okay, so my suggestion will be there is to compare this magnetic and dielectric material. Okay, so here if you are finding the value of mu 0, then at the same time you have to revise the value of epsilon 0 also. Okay, so what is the value of epsilon 0? Epsilon 0 is nothing but 8.854 into 10 raised to minus 12 coulomb per meter. Okay, so this is the value of epsilon 0, and here in this magnetic material we have to find out the value of mu 0, and which is nothing but 4 pi into 10 raised to minus 7, and its unit is Henry per meter. And again from this expression, that is mu is equal to mu 0 into mu r, we will derive one small relationship, that is mu r is equal to mu divided by mu 0. So that mu r is known as relative permeability of a magnetic material, and that is defined as the ratio of permeability of a solid material mu to the permeability of free space mu 0 is called as a relative permeability. Okay, so here is a expression, that is mu r is equal to mu divided by mu 0. Okay, so like in case of dielectric material, we are having the relationship, that is C divided by C0, which is epsilon r. Okay, so in the similar way, here mu r is nothing but mu divided by mu 0, and it is a ratio of the permeability of solid material mu to the permeability in free space. So that is nothing but relative permeability of a magnetic material. So here that relative permeability is given or denoted with the help of symbol mu r, and we know that for air or vacuum the relative permeability for magnetic material is 1. Okay, so for air or vacuum. So the again, if you are observing the expression for the relative permeability, which is given as mu r, mu r is equal to mu divided by mu 0. So if you are observing these two quantities, again these two quantities are similar to each other, and hence they will cancel out the term each other, and finally it is a dimensionless or unitless quantity. Okay, so relative permeability is a unitless or dimensionless quantity. Keep in mind that. Again, so this is all about the first parameters in case of magnetic material, that is permeability. Now we will move towards the second parameter, that is magnetic dipole moment. Okay. So before magnetic dipole moment, quickly revise the parameters which is present for the dielectric material is dipole moment, which is denoted with the help of symbol mu, and which is given as q into d, means product of the charges and distance between them, and their unit is coulomb meter. Okay, so this is all about the electrical dipole moment. Now here we will understand the importance of magnetic dipole moment. So for a bar magnet having two poles of opposite nature, then the magnetic dipole moment is defined as product of pole strength and distance between them. Okay, so this is important line, that is product of pole strength and distance between them. Okay, likewise in case of electric dipole moment, we are having product of charges and distance between them. So here in case of bar magnet having two poles of opposite nature, then the magnetic dipole moment is defined as product of pole strength and distance between the two poles. Okay, so here some simple formula is there, that is mu m, which is nothing but magnetic dipole moment. So this mu m stands for magnetic dipole moment, m is a pole strength, and d is nothing but distance between the two poles. So it is a vector quantity and always directed from south pole to north pole. Okay, so keep in mind that magnetic dipole moment is a vector quantity and which is always directed from south pole to north pole. Okay, so already we have covered the two parameters regarding the magnetic material. First one is a permeability and second one is a magnetic dipole moment. Okay, so in short, here we will have one short differentiating or comparison point between electrical and magnetic dipole moment. So first point regarding the electric dipole moment is that it is a vector quantity which is directed from negative to the positive charge, whereas in case of magnetic dipole moment it is again vector quantity and which is directed from south pole to the north pole. Second point is that it causes electric field. So obviously, whenever there is a formation of electric dipole moment, then these two charges will form an electric field. Whereas if there is a formation of two different poles, that is south and north pole, then they causes the generation of magnetic field. Okay, so this is the simple some comparison point in between electric dipole moment and magnetic dipole moment. Now, third parameter of magnetic material is magnetization. Okay, so in case of electrical, we know that third parameter is polarization, which is denoted with the help of symbol P. And polarization is nothing but formation of formation of electric dipole moment mu per unit volume V is nothing but polarization in a material. Okay, means formation of two opposite charges is nothing but polarization. Now we will see the magnetization in case of magnetic material, and which is analogous to the electric polarization. Okay, so magnetization of a solid magnetic material can be defined as total magnetic dipole moment per unit volume. Okay, again same total dipole moment per unit volume. Only the difference is that instead of electrical or dielectric, here is presence of magnetic word. Okay, so magnetic dipole moment per unit volume is nothing but magnetization for an magnetic material. So here I can write magnetization m is equal to magnetic dipole moment mu m per unit volume. Okay, so magnetization is defined as the magnetic dipole moment mu m per unit volume is nothing but magnetization. So here we will have one small derivation which will represent the formation of magnetization inside any material. Okay, so let's means practically if I am having iron material and if I want to test how much magnetization will get transferred in that iron material, and that can be calculated with the help of these simple derivations. Okay, so let's have one proof. So if a solid is placed in a magnetic field, then magnetic field can gets redistributed as compared to its original distributions. So if you are not getting this, once again try to read it slowly. So if a solid is placed in magnetic field, it means that I am having such type of magnetic field present here, and I am placing another magnetic material in between that magnetic field. So let's consider this is one piece of iron material which is placed in magnetic field. So what will happen? It can get redistributed as compared to its original distributions. Okay, so like this, if I am after placing this magnetic material, it will get redistributed. Okay, so redistribute means what? Instead of crossing this material, they will try to move like this. Okay, so I will choose different color. So like this they will get redistributed, or these magnetic lines will get redistributed in this way. And if this material is having higher value of permeability, then obviously some lines will get crossed through that material, and due to this material will get magnetized, and again it will produce its own magnetic field. Okay, so that we will see in next line. The resultant magnetic field is given by Sum of the primary field B0. Primary means what? Which is initially applied here. That is primary field B0 and field created by solid. So here field created by solid means this material. So here this solid material is nothing but this field created by this solid material. Okay. Ag- So again, in order to understand here, I will quickly show you if I am having one solid magnetic material. So let's consider here solid magnetic material small s is placed in a magnetic field. So obviously some magnetic field will move like this and some magnetic field will cross that material, and due to this material will get magnetized and it will produce a magnetic field that is Bs. Okay, so here it is a Bs and here it is the original magnetic field density B0, and based on this we have to derive one small derivation regarding the magnetization. Okay, so here is the magnetization. So total field B is nothing but formation of or combination of B0. This is the initial field B0 and B solid means the field produced by this solid material which is externally placed in a magnetic field. So we know that the relationship between magnetic field strength and flux density, okay, so which is um, seen in previous expression. Okay, so here b0 is nothing but mu 0 into h. We know that b is directly proportional to h. Okay, so already we have discussed this, and based on that here I can represent b0 is nothing but mu 0 into h and b solid is equal to mu 0 into m. M stands for magnetization in that solid material. Okay, so after taking common mu 0 I am getting b is equal to mu 0 in a bracket h plus m. Okay, so h plus m, where this mu 0 into m, now if I am uh, discussing this mu 0 into m is an extra magnetic field associated with the solids. Okay, so already we have discussed this, that bs is nothing but extra magnetic field which is generated by on that material. Okay, so finally m is nothing but magnetization of that solid. Hence finally this expression after here I can write b is equal to mu 0 in a bracket h plus m is proved. H plus m means obviously here I want to represent that B is directly proportional to H, but there is formation of magnetization in a solid material M. So here in short we are representing that B is equal to mu 0 in a bracket H plus M. And also we know that one more relationship, that is B is equal to mu 0 into mu r into h. Okay, so obviously again this proportionality constant is represented with the help of symbol mu. So here you can write this b is equal to mu into h, and this mu is nothing but mu 0 into mu r into h. Okay, so this is the general expression for the magnetic material which is shown here. Okay, so here we have proved the magnetization M, how the magnetization is formed inside a solid magnetic material. Okay. Now from this we are going to discuss the next parameter for the magnetic material, and we are using the same expression which is used for the magnetization. We are taking the help of these expressions in order to derive the fourth expression for a magnetic material. So here again short expression is given. So we know that mu 0 into mu r into h. So what is this? This is the here b is equal to. So we know that b, this value b is equal to mu 0 into mu r into h. So I am putting this value mu 0 mu r into h here. So what I will get? So this is explained here. Mu 0 mu r into h is equal to mu 0 into h plus mu 0 into m as it is. Okay. Now here just do the some simple mathematical arrangement. So cancel out the mu 0 term. So remaining is m is equal to mu r into h minus h. So I will clear the screen so that you will get clear. So here mu 0, mu 0, mu 0 will get cancelled, and I can write m, this magnetization value of magnetization m is equal to mu r into h minus this h will get here. So it will be minus h, and finally m is equal to mu r minus 1, take h common. Okay, and here again shift this h to this side, so m by h is equal to mu r minus 1. M by h is equal to mu r minus 1, and this total expression that may be m by h or mu r minus 1 is known as a xm. Okay, so what is xm? Xm is nothing but susceptibility of a material. So I can write here xm is equal to, that may be m by h, or it may be that is xm is equal to mu r minus 1. Okay, so this is the expression for the xm, that is m by h or mu r minus 1. So again here in shortly, if I am having xm is equal to mu r minus 1, then someone can write a mu r is equal to xm, sorry, 1 plus xm. Okay, so this is shown here. Okay, mu r is equal to 1 plus xm. So xm is independent of material. So xm is a susceptibility of material. Okay, so susceptibility of material, that is the fourth parameter which is applicable for the magnetic material. Hence it is proved that is mu r is equal to 1 plus xm, that is relative permeability for magnetic material is given as 1 plus xm. So the magnetization m of a material in terms of magnetic dipole moment, m is equal to n into mu m. So this is the another definition, that is magnetization is nothing but number of dipole moment, that is magnetic dipole moment present inside that material, or formation of magnetic dipole moment in the solid magnetic material is nothing but magnetization of the material. Okay, like in case of polarization we can say that formation of electric dipole moment per unit volume. So in the similar case I can say that number of magnetic dipole moment per unit volume is nothing but magnetization. And now we will move towards the last property of a, or parameter of a magnetic material is nothing but magnetic susceptibility. And already we have derived the discussion for the derivation for the magnetic susceptibility. So for magnetic material, it is found that magnetization m is directly proportional to the magnetic field strength h. Okay, so this is derived expression in previous slide, that is magnetization m is directly proportional to the magnetic field strength, and it is also defined as the ease with which the material can be magnetized. Okay, so this is the very easy definition for the susceptibility. Like this, it is a ease with which materials can be magnetized, is with which material can be magnetized. This is nothing but magnetic susceptibility. Okay, or we can say that magnetization m is directly proportional to the magnetic field strength h. Okay, so this is also magnetic susceptibility, and from that we can derive here expression magnetization m is directly proportional to the field strength h, where proportionality constant is nothing but xm, and xm is nothing but magnetic susceptibility. So xm is equal to m by h, or you can say that xm is equal to mu r minus 1. So all these two expressions are derived in just previous slide. Okay, so thus the magnetic susceptibility can be defined as magnetization per unit magnetic field strength. Magnetization per unit magnetic field strength. So this is the definition for the magnetic susceptibility, that it can be defined as magnetization per unit magnetic field strength, means xm is equal to m by h, and it is a dimensionless quantity, and also it may be positive or negative. Okay, so the value of susceptibility may be positive or negative, but it is a dimensionless quantity as it is a ratio of magnetization and field strength. Okay, so these two terms are again similar in case of magnetic material. It is independent of magnetic field strength H in case of weak magnetic material. Okay, so if you are considering very weak magnetic material which cannot be generally magnetized, and in that case, which is independent of external magnetic field strength, means you can, if you are applying strong magnetic field strength, then also there is a less, or there is very low formation of magnetization or magnetic dipole moment in that material, and hence such material is known as a weak magnetic material. So in short, it is independent of magnetic field strength. Yeah. So here, small comparison between the permeability of magnetic material and susceptibility of magnetic material. Okay, so permeability is nothing but the property of material which allows itself to get magnetized. The property of material which allows itself to get magnetized is nothing but permeability, whereas magnetic susceptibility is nothing but it is proportionality constant which indicates degree of magnetization. Okay, so means at what amount that material can be magnetized is nothing but magnetic susceptibility. It is a ratio of B by EH, okay, field strength to the, sorry, plus density to the applied field strength, and here it is a ratio of M by H, that is magnetization to the applied field strength. So unit of permeability is Henry per meter, whereas susceptibility is a dimensionless quantity. Okay, so this is the simple comparative points between the permeability and susceptibility of magnetic materials. So finally, we will conclude our sessions. So at the end of these sessions, we are able to find out the different parameters of magnetic material, and based on that parameters, we can compare these parameters of magnetic material with the dielectric materials. Thank you.